Okay, so pullback. So remember last time I explained what a connection is, and I explained that it's very easy to pull back connections. And then now I want to explain pullback firstly between affine varieties, and then I'll explain that it glues to give a functor between for any morphism. So remember the blurb, which is that we get mileage in algebraic geometry out of morphisms. And so we need to be able to move D modules between spaces. Doing so is hard because functions are contravariant. You can pull back a function, you can't push forward a function unless you're in some special situation. Whereas vector fields are covariant. You can push forward vector fields, you can't pull back vector fields. Yep. Yeah. One form's a little bit like functions. You can pull back a one form. One form's a dual to vector fields. They can push forward vector fields. And so, like, if you think about D modules, it's kind of a mix of functions and vector fields, and you can pull back one and push forward the other, and so it makes things hard. And I think in later lectures,
so you can't actually push forward, but you push forward tangent vectors.
Yeah, exactly. You can push forward a tangent vector, but pushing forward a vector field is problematic. Exactly. Yeah. Yeah, which is the algebraic fact that you can't, like, if you have a derivation, it doesn't. Yeah. So if we have. So here we have a map of affine schemes. And then we have an induced map on functions, A to B. And this is pulling back one forms. And yeah, what Chris is saying is that if I have a tangent, a vector field is a map from here to B, and I can pull that back to get a map from here to B, and if I'm lucky, it lands in A, and then I get a vector field on A, but that may not always. Yeah. So this is the affine case. Okay, so here I have F. So A is functions on Y. This is also what I call O of Y. I can pull back. Pull back on. Okay. Now, and I explained last time that a dy module is the same thing as a fuzzy coherent D M with flat connection M and now we're just going to do some commutative algebra and see that there's a natural way to pull back flat connections. So all I'm doing is a fancy way of saying, you know, remember last time we had connections, which once we choose a basis is just a n by n matrix of one forms, and then I can just pull back one form. So I get a new matrix, that's the matrix of my pullback connection. And now I'm just doing a fancy version of that, fancy commutative algebra version of that. So I take, so here, so we start with my M, and then I have F upper star of M, which is B tensor over A with M. And then I have a map from here to B tensor over A with, so this is over A. N is D X Y tensor over F inverse Y. So if you chase through the definitions, you get a definition of the pullback, and this is very useful for theory. So,
zoom back up and maybe you can just summarize what we did in the last lesson.
sure. So you want me to pull back a little bit? So yeah, so summarizing, this was last week we saw how to pull back connections. I've got a matrix of one forms, I can just pull back. My one forms, I get another matrix, that's my pullback connection. And now we saw that this, like the notion of a vector bundle with flat connection kind of doesn't need that something's a vector bundle. Okay? So we can formulate like quasi-coherent sheaf with flat connection, and we get this gadget, and this is equivalent to it being a D module. So a D module is something where I can differentiate sections. And then, and so taking this point of view gives us a pullback of D modules in the affine case. Just chase through some formulas. This is kind of every point here you're doing the obvious thing. Okay, so this we get our first definition of pullback. Now there's another definition which is some kind of version of the chain rule. That's useful for actual computations. Probably the most useful for computations, but I don't have like a literal vector bundle with flat connection. And then there's another point of view which we'll emphasize much later, but I'm just kind of putting it on the board now so that people are used to it at some point, is that we have this universal thing. So basically, in non-commutative algebra, somehow bimodules play an extremely important role, because bimodules are somehow some very useful way of thinking about functions. So I think about a bimodule kind of like, you know, in linear algebra, you have linear maps, and that's fine, but sometimes it's really useful to write down matrices. And in non-commutative algebra, you have functors, that's fine. Generally, you can't get your hands on a functor, but you can get your hands on a bimodule. So bimodule is great. And if you work on schemes relatively, a bimodule will be like a sheaf of bimodules, and this is what we get here. And this bimodule is a very useful tool for realizing pullback of modules. So just to give you a taste of why this is so useful, like it's very clear now how to define a vector driver candidate. Right. So it's not entirely clear to me, if I don't use this definition, how I can get the right functions for pullback of modules.
But why with that kind of scheme, why has the well?
As the requirement.
Like, so to define the drive pullback, we need the drive average and things like basically that. Why is it clear that in the scheme line?
Just because it's flat resolution, because this is flat resolution. Anyway, we'll discuss this further. Okay, so this is pullback. And now I just want to explain a little bit of philosophy, kind of teaching philosophy, which is that I feel that like the vast majority of the notes on D modules just like we'll do pullback, and now we'll start doing push forward. And you can do a whole lot of like crazy homological algebra. Reciprocity. It's like this perfect gemstone, which is totally impenetrable. Yeah. And so I feel like as mathematicians, it's our duty to fight against this technical edifice and not create these like enormous mountains that are impossible for students to climb. Like to actually try to explain what's going on. And of course it's hard, but I think it's worth it. So that's end of rate. Yeah, so what I want to give you is a rough picture of what D modules look like on A1. And I'm hoping that within a few weeks, this will not only be a rough picture, but you'll have a precise one. Also, you know, I think it's a very interesting discussion about what is useful in mathematical communication and what kind of community we would like to have. So if you have any comments, I would love to hear them. So rough picture of D modules on A1. On A1, yep. Let's see. So firstly, I hope that the following is basically known to you in some form. So what about coherent sheaves? Okay, so what is a coherent sheaf on A1? This is the same thing as a CX module. Finitely generated. Jinx generated CX module. And then by the fundamental theorem of modules over a principal ideal domain or whatever they call it, this is isomorphic to Cx to the n plus some over Cx modulo x minus ai to the ny. So for I equals 1 up to L and ai C, certain points, and M on the equal. Okay. And how do we picture this? So I remember, when I first learned this, I learned this as an algebraic statement. But once you learn algebraic geometry, you get this beautiful kind of geometric statement, and then somehow you can never forget it, which is that you have like, I imagine that C of x is kind of like this vector bundle floating everywhere. And this is what C of x looks like. And then I have these skyscraper machines. So this might be C of x modulo x. So this might be point 0. And then I might have C of x modulo x minus 2 to the 7. And I imagine this is a thick point here that's kind of 7 degrees thick sitting at this point. Yeah. And so this is what a coherent sheaf looks like on the affine line. And then, so this is the vector bundle part. And this is the torsion part, and this is canonical to submodule, this is canonical to quotient. So you kind of should think that these are interacting in some way. And yeah, we also have it's important to remember that finitely generated is a strong condition, and you also have things like Cx inverse, which is quasi-coherent. Okay, so it's a Cx module that's not finitely generated, and I don't quite know how to think about these things. I think of them a little bit airy-fairy, kind of living on this space. So now, what about coherent dx modules? So now there's two options. So I can think about dx, but in a certain sense, dx is too big. And I hope to explain in further lectures why that's the case. But one way to think about, so what I describe is D modules M, which are generated by M1 up to Mn. So they're finitely generated by certain elements such that the annihilator of each Mi inside dx is not 0. Okay? So what this says is that so it's generated by elements satisfying some differential equation, which is not trivial. Yep.
Equals 0.
Not equal to 0. Okay. So this seems to me, with the motivation from differential equations in mind, this seems to me very natural. Yeah. We only want to consider modules which are generated by things which actually satisfy some non-trivial relation. Yeah. And this means that M is polynomial. Okay, and we will see later what this means, the actual meaning of this word. Okay. And then we'll also see later that this implies that there exists U in X, Zariski open, such that M restricted to U. In other words, we've explained how to pull back D modules now. So this means M pulled back to U is coherent over O of U. Now, just a little are you awake question. What was the exercise there? What do we know about D modules which are O coherent?
but and it's effective on it's totally agree.
Exactly. MU is locally agreed. A vector bundle. Okay. So this kind of looks similar to over here. Okay, but it's already like, you know, insanely much more complicated. So U means that we remove finitely many points. So there's Zariski opens inside C without finitely many points. Here's so MU is a vector bundle back connection. Okay. So here we have essentially a vector space, and you know, if you've been doing the exercises, you've started to come to terms with the fact that a vector bundle with flat connection is a vector bundle in which nearby points are canonically identified. Like there's canonical identifications between the fibers of nearby points. Okay, and so you know, for example, I can have monodromies around these points, but also I want to emphasize that like this is not just determined by its monodromy away from regular singularities cases. That's basically some differential equation on a vector bundle away from one of the points. Okay.
And when you wrote this, you meant really x equals a1 for right? This condition being called holonomic.
Absolutely. Yeah. So this is true in dimension 1. Okay, so in higher dimensions, so another word for holonomic is maximally overdetermined, which means that every element satisfies the most number of differential equations that it possibly can. That's what a holonomic system is. And in dimension 1, it turns out that there's essentially only, around each point, there's only one, you can at most satisfy one differential equation. But we'll come to that much later. So at singularities, M is never coherent. Okay, like that's just absolutely formally follows from what I said before. But I just want to emphasize that, like, you know, at these points, you have something that's like, it's never going to be a coherent sheaf. It's never going to belong to that picture over there. Okay. So, what about? So this should give you the kind of generic picture of what a D module looks like. And now we can ask, what about D modules? What about the analogs of skyscrapers over there? What about D modules? Supported on the point. And then there's this beautiful D module, which we haven't really met yet, I don't think, which is called delta 0, which is D of A1 modulo the x times x. Now, as a so if we think about the Weyl algebra, so we're on A1, so this is just polynomial ring in one variable together with a delta. So and we can write a basis of our Weyl algebra either with deltas on the left or x's on the left. And so once we mod out x, this says that this entirely consists of deltas. So this is a direct sum from I equals 1, 0 up to infinity of C delta to the I as a vector. And exercise, so there's is that so that one has a short exact sequence of D modules Cx, so this is the D module in a natural way, just by differentiating in x, goes to Cx x inverse. And the quotient of this, which is Cx x inverse modulo Cx, is isomorphic to delta Z. So this implies that this is not a coherent sheet, but every element is annihilated by x. So, sorry, every element is annihilated by some power of x. So this implies that delta zero is supported at zero. And two, so this is like a remarkable difference to the case of coherent sheets. So imagine that I look at coherent sheets supported at zero. I've got this guy, but then I've got Cx modulo x squared, x cubed, etc. So I've got a whole lot of thick points supported here. Yeah. And the second exercise is that this never happens, this phenomenon doesn't happen in D module land. So that show that any coherent dx module supported at zero is isomorphic to delta zero, the end assumption. And this is kind of remarkable semi-simplicity. And then final exercise is that recall our D module M lambda, which is isomorphic dx modulo xd minus lambda. Okay, so this is also dx times this function z to the. So show that x1 of m lambda with delta zero is equal to x1 of delta zero with m lambda equals zero if lambda is not an integer. So, you know, it's very normal in representation theory in related fields to first have some classification of something like simple objects and then see how they fit together. Okay? And I haven't said it yet, but this NU can be made into a simple object in a canonical way on all of X. So there's a way of extending NU in a canonical way over each of these singularities to produce a simple object. And also we have these delta zeros, which are also simple objects, sitting at each of these points. And then what this is saying is that for certain monodromies around here, these do not interact. There's no extensions between them. And what we'll do later on is study much more the glue that fits these things together. Okay? So it's kind of like this is where D module land really takes off, because if you're just looking on the open bit, this is just vector bundles and flat connection. Yeah? And that's, you know, people have been studying that for many, many years. But now the question is how do kind of vector bundles with flat connection propagate into singularities? And that's when like the real theory of D module starts taking off. So in some sense, like the first genuine example of a D module that's not a vector bundle with flat connection, you've just seen it's delta zero. Yeah, this skyscraper. Now, further comments. Yes, and maybe yeah.
Hey, Geordie.
Yes.
Just a question. This delta zero, would this be related to the sort of Dirac distribution?
Exactly. Yeah. That's exactly what you should think about that. What made you think that?
Mostly all the results, because I know that the only sort of differential operator in the distribution which is supported at the point are really just those combinations of the Dirac delta. And it felt very similar.
Yeah.
I just like the language of it being sort of a point and knowing that D modules go to distributions.
Yeah, exactly. So that's the next remark. Is that one should delta zero as Dirac delta function. So firstly, reason one is that delta zero is isomorphic to dx modulo dx times x. So the solutions is dx times. And in general, we've seen that when we take this quotient of the left ideal like this is like asking for the D module corresponding to the solutions of that differential equation. And Dirac delta is a solution to x times delta equals 0. Another very beautiful way of thinking about this is that I'm not sure we'll have so much to say about this, but we have the Fourier transform, which in D module language is the innocent looking operation on A1 that sends x to delta and delta to minus x. And then, so this is called, let's call this Fourier transform. So it's induced by an automorphism of the Weyl algebra, which has this effect on generators. And if you do Fourier transform of this D module, we get dx modulo dx times delta, which we've seen is the D module corresponding to the constant function. So in other words, and this mimics the fact that the Fourier transform of the Dirac delta function is the constant function. Okay. So, and there's also several other reasons to think that this should be Dirac delta function. And also for later, there's no reason to consider delta zero just at 0. So we define delta lambda to be D modulo x d x minus lambda. And generally on any manifold or on any smooth scheme, we have a delta D module supported at any point of that scheme. Yeah, so I was going to explain kind of applying the solutions function to the delta function, but I think I'll skip that for the moment. So now I just want to give just a few examples of pullback and then I'll finish. Are there any questions?
Is there a way you can compare this with functions, like you would integrate against the delta function?
So you want a kind of version of the formula that the integral against the delta function puts. What does it do again? Oh, it just takes the value of the function at that point. Yeah, so this should just be, yeah, so we haven't explained why, but there's a tensor product on D modules, and tensoring with the delta function is basically taking the stalk of the D module at that point. And so it's exactly analogous. So tensor product of D modules categorifies product of functions. Yep. So if I have two functions and I take their product, what's the D module? What's the differential equations that they satisfy? That's the tensor product across the modules. Okay, so now pullback. I just want to show you something funny before we finish. So this is just an example. We take the map from C to C given by x goes to x squared. So this is vector C x and this is vector y. So it's just the squaring map. And the question is, so firstly, I just want to remind you of what it looks like for coherent sheets. Okay, so if we pull back, and somehow I hope that last time, so when we pulled back connections, somehow what we saw is that we get a connection where we just run around the monodromy twice. So if we pull back something, yeah, so I'm not gonna pull back connections again under this map. I'm just gonna pull back skyscrapers because it's funny. Okay. So firstly, what does this look like under coherent? So here's x, and here's y, and here I have my square root. And if I take f upper star of the skyscraper, so C, y, this is the same thing as C of x tensored over C of y modulo y minus gamma. And basically, this means that this is isomorphic C of x modulo x squared y. And so there's two cases. So if gamma is 0, I just get C of x modulo x squared. And if gamma is non-zero, I get C of x modulo y minus alpha plus C of x modulo y plus alpha. Sorry, x. Where, yeah, so I take this equation, either it's got a repeated root, in which case I get a thick point, or it's got or this number is non-zero, in which case I factor this into two pieces, and then I get two skyscrapers, where alpha is the square root of gamma. Okay, so pictorially, if my gamma is out here, so then I get the two square roots. So this is meant to be just a skyscraper here, and then I pull it back and I get the skyscraper here. Whereas if I pull back this, then this is 0. Then I get this point twice. Okay. And this is kind of a very important fact in algebraic geometry. So this is like it's to do with intersection multiplicity and stuff like that. The fact that so here when I pull back, I get 2 points. Here when I pull back, I get 1 point. And if you're not careful, this looks like problematic because we kind of have 2 points and then suddenly they're 1 point. But these points actually happens twice. So this has multiplicity too. And so a whole lot of formulas work out and stuff like that. So it says definition of another way of phrasing this is that if I have a parabola and I intersect with a line, then generically I'll just get 2 points. But if I move my line so it's parallel, I get a thick point. And if I interpret this thick point correctly, then I still get the right answer that the intersection of this line and the parabola has multiplicity too. Yeah, and we have exactly the same phenomenon going on here. Okay, and now if I were to put a thicker point in here, I just get two thick points with the same index if I'm not at 0, or I get a thick point of double thickness if I'm at 0. So now let's do let's pull back the Dirac delta function, and I think it's nice, like try to guess what you think the answer is going to be. So yeah, as Chris said, so what about, so y is actually my low one, so I'll switch to y matrix. So let's first compute the pullback of delta 0. So we have the following exact sequence that we established in the exercise. And now we have pullback as coherent, pullback. Sorry, this should be y. Yeah? So everything's flat, and so I pull back as coherent cheese, and I just get C of x. This is C of x. Inverse goes to come back again. And now we know that this has a unique. So this, but again by the exercise, this has a unique D module structure. So hence this is delta 0. And one way to think about this, so it's kind of it's very funny from a coherent sheet point of view, I think, that we pull this one point back. So we pull this delta back, and we just get one copy of it. But one way to think about this is that, well, one way to think about this is it's kind of like infinity plus infinity equals infinity. Okay, because when I pull back each of the approximations of this thing, so this is the limit, delta 0 is the limit of Cy mod y to the n. And each time I pull back at these, it doubles. And so, but when I take the limit, I just get like infinity plus infinity. And then maybe another, yeah, probably like another exercise. Is that f upper star of delta gamma is delta alpha plus delta minus. Okay, so it's like subtly different to the case of coherent sheaves in a very important way. And this also starts to resemble much more what looks like the pullback of constructible sheaves. And that also we will see later on why that's the case. Yeah, I think that's it for today if there's no questions.
So I'll start. I'm going to be talking about left versus right D modules. Maybe we'll finally understand the exercise in week 1 of which line models on E1 admit the D module structure. Also, I'll just say this is reasonably technical, so I'm going to try and give the overview of how it works and then indicate the proof. But some of the parts of the group I've left as exercises, which I really encourage you to do because they're not that hard. And it won't be enlightening if I do one more. It would be very helpful to do it yourself, especially if you want more getting used to using coordinates and actually verifying these things and just actually manipulating D modules. It's not something you can do in your head. I mean, it's not something I can do. So let's learn how that is. Okay, so I'm going to start with a general construction, which I have never seen before this, but it's totally chill. Which works in any monoidal category where there's an object that's invertible under multiplication. So for us, L will be a line bundle, and A will be an OX algebra. Okay, I'm going to be deliberately vague with what these things are, so you can see how the general categorical formalism works. So then L tensor, and all of my tensors will be over O of X. Okay, so we're working in the monoidal category of O of X module. Okay, I just don't want to try to write it, but it is important. So this is also an O of X algebra. Okay, so I need to tell you what the algebra law is on this. This is a just a sheet. So on sections, we want to know how to multiply, and this would be defined over U, or the extended as G times prime, Y, E prime, this is S, that's X, E prime, where I need to tell you what this bracket is. The bracket is, by definition, the isomorphism in these guys, tensor product to O of X. Okay, so this exists because it is a invertible object, tensor of the opposite line.
Or the dual, I mean,
Sorry, the dual.
yeah, I think this is just the dual parent.
Yeah, it's just the dual parent. There's nothing new. Okay, so now, at this level of generality, note that we have the following. So, A over OX modules, we actually have a equivalence between A over OX modules and this twisted OX modules. Okay, how do we do this equivalence? Well, M goes to L tensor M. Okay, and if we know how A acts on this guy, how might L inverse act on L tensor M? Well, you do the canonical pairing on those first two things, and then you act by your section, and then the other part can move. Okay, would anybody like me to spell out that more, or is it pretty hard to do? Yep, more spelling out? Great, okay. So, in other words, we want to define an action of this algebra on this module. Okay, so we're going to define it locally, because we have, we're dealing with sections of sheaves. So, say, if S and T are sections, we want to define how this thing acts on, right? What would be a section of this? Well, if we picked a section here of L, we can use this section to like orient L. I mean, it doesn't really matter to me like that. So, where this is some other section of L, we're defining this to be pair these two things together, and then multiply by X. Pairing E prime. And so you can see X knows how to eat elements of M. This is an element of X, so it knows how to act on M. And it spits out something. Okay? And we can check that this is an equivalence, because if we take L dual or L inverse, we go back the other way. Okay. Right. So now, what follows? We're going to define omega x to be the top exterior power of x, also known as the coherent dualizing sheaf of x. So this is, in particular, it's a line. So this is the top exterior power of the cotangent bundle. Shows up in duality formulas. It's like a canonical line model that we get associated.
Do you want to use a little omega on the left?
What's that?
Did you want to use a little omega on the left?
What's that?
Did you want to use a little omega on the left?
I mean, I want to, but the sources don't, and so I won't. But I do want. Yeah, it's like I'm sticking with it because actually all of the sources I read that use that. It's just
it's really confusing. That looks like a the only differentiation is there's a one. You're saying.
Yeah.
Okay.
I mean, like.
That's unfortunate.
I mean, it is really unfortunate, but I don't know whether like changing it now would make it harder. Maybe just it is very important that there is no symbol here, but also from context we can you can tell if you've got a connection, then it's going to be a big thing, and if you're just tensing any random thing, you're not going to tense any random thing with code. But I agree, this notation is terrible. It is terrible, but I'm not brave enough to fight against it just yet. Okay, so now the main theorem, which maybe I'll just put up here. This theorem is that dx op is isomorphic to x, and so dx is the omega inverse as Pullbacks algebra. Okay, so now if we believe this, then we see, okay, given a left D module, we want to cook up a right D module, aka a dx op module. So by this, we just tensor with the dualization. So this is a very simple way to get it to go between them, just by tensoring with this line and tensoring with its inverse to go back.
So dx op is just turning the left module into the right module?
No, so dx op is a general, for an algebra, you put a new multiplication law on it, where you say x dot y is yx. Okay. And then it's an easy exercise to show that an a op module is a right angle. So it's this left and right can also be phrased as op on your algebra. So yeah, left dx op module. Same thing as right. Okay, and I'll spell it out, assuming we have this. Then, when we unravel the definitions, this just becomes we have a dx op action on this line bubble, and to go between left and right D module. So we want to say, given the D module, how do we get the corresponding? Given the left D module, how do we get the right D module? Well, let's say on the left, then we want to define we basically define it using this like. So in particular, we want even a top. We want to know how to act on it. And find specifically on the right. Okay, so this is essentially saying this big process for this thing. Once you unravel the definition, tells you can get an action of the F plot on the sheet. And then this action gives you literally how to go from left to right. You tensor with this line model, and then you action. Okay. Any questions about?
So where does the action of the x op on omega x come from?
Right. So one way translate it. So if we have this item, then I haven't told you how to make that one. This is like more than this like no. So I will this is called a once we have this action, you'll know exactly how to get it from that. So, not a right dx action on omega x. That's our goal. I'm going to start by giving a new definition which will lead to actually describe this action. Okay. So this is a thing from differential geometry. So be a vector field. And so basically there exists a gadget called a Lie derivative. So this is something that exists in differential geometry. It also exists in here, and we're going to need to use it. So I'll tell you what it is. A C endomorphism of, okay, now we are really acting on all of the exterior powers, okay? Of degree 0. So it acts on all of these exterior powers, but it preserves them, like it sends the I ones to the I forms 0. Call it LB. Okay, such that. Okay. So LB 1, where do you make it 2? LB make it 1 plus. Okay, so it like acts like a derivation on this alpha. For omega I in the like greater than or equal to 1. Okay, so this is not how it acts on functions. Okay. Okay. In particular, like this is wedge, not just function. Right? This is how it acts on functions. Oh, we have a vector field, a function. We're going to spit out a function. This is just that vector field applied to that function. And last thing is that it commutes to the exterior derivative. Okay. So I said definition, but this is more of a like definition proposition, which is that there exists unique endomorphisms of this sheaf that are characterized by these. So you want to apply LV to some form. If it's in dimension 0, you know how to do it. If it's in higher dimension, you also know how to do it using this and using the fact that it commutes. So to verify that it's unique, you need to show, like, I think you need to assume the Poincare lemma that like every function is locally even to D.
Yeah, but every function is every one form is locally linear combination of functions times d of something. So it's OX linear in the OX linear in
Yeah.
you can deal with things in the form like F times dg. So I think that first formula you don't need to assume it's higher degree.
Yeah.
No, this is just the line of inference.
Yeah. Okay. Because that was because I was I'm trying to verify this. I was like, wait, pass to like analytical proof of this. But okay, fantastic. So this holds in general, which tells you how to act on one forms, because one form's a wedge is 0 and dx. Okay, fantastic. Right. So the now exercise. So show LV is uniquely defined by these properties. This isn't particularly difficult. So sit and think why it's uniquely defined, or assuming it exists, sort of why it's defined. Okay. However, the non-trivial part and show that LFB is equal to LV of F as endomorphisms of the top forms. So, this in particular does not hold the lower thing. This is like when it acts on the top piece of this graded exterior thing, you have this not commutativity, but it sort of flips over. Okay, so how are we doing the time? Because if there's lots of time, I might prove some of these. But if there's not much time, okay, it's 4:07, so maybe afterwards, if people want to try and do some exercises, we can go over how to actually prove these. For now, press on, but does anyone have any questions? So now I'm ready to tell you the right action. So we find the right action by, so we know, well, on O of x, it's just multiplication, right? O of x just normally acts on dot forms. So we need to define how vector fields act. So omega dot v is negative this LV applied to omega. Okay, so this is the definition of the right action of your right E module structure on top. Okay, so now I'll state what needs to be checked to check that this is in fact a right action. So we would need to check, we just need to check that the relations are satisfied, right? So we need to check that, and I've rewritten them to make it a little clearer. For any form, function, and vector field, we have B, BF times omega. So now, I realize normally when we present the Euler algebra, you pick coordinates and you say x1 up to xn with these given relations. But it's also worth knowing that there is this coordinate independent way of stating relations, right? The coordinate independent thing is Alex. That. Okay? So it's generated by vector fields and functions subject to these relations. When we translate these relations into this to check that it's right action, we just need to check that it's on. Okay, fantastic. Now, proceed to do that. And now, admittedly, this isn't particularly enlightening. So maybe I will actually instead give them an exercise. And then I'll prove that assuming the exercise. So you can do the exercise and the enlightenment. Instead of just prove that. Exercise, the coordinates 1 up to xn. We have L I F 1 10 equals x I F times and so this is, viewing xi as a derivation, and we're applying it to f. Maybe once you picked coordinates, if you're saying c to the n, this is like, the derivation partial derivative. But yeah, remember, this is just not a vector field, and this is just, you apply that vector field to this, and in the case, and so I want to point out though, if once we picked out coordinates, this is how these vector fields act on top dimensional forms. However, if I picked a different vector field, it would not act in this way on top dimensional forms. So this is something which confused me greatly, which is how do you describe how these things act in a coordinate independent way? Because it feels like if you want to describe how vector fields act, there's not a unified way to do it. I'm telling you how these xi's act, how everything else acts, it generates everything. But like, is there a unified way in which vector fields act? And the answer is no. And this is a sort of point which I will hang on a little bit about, which is that so within V of x, there's a canonical left submodule. Okay? Well, there exists a canonical left ideal, which is x or vector fields V. Now, and this is sort of what we use to define our solutions function, flat sections. Right? We look at the things annihilated by the section. However, there is no such right ideal. Right? In other words, coordinates, when you change your coordinates, you mess with vector fields on the left by functions. So, in particular, this is a right module. So, and there's basically no like coordinate-free way to say what vector fields are from the right. If you change your coordinates, you will genuinely change that idea. So this is like, one slogan you could say is that right B modules do not have flat sections. That doesn't make sense. Because for flat sections to be like a, it's like there is no coordinate independent thing on the right which plays the role of flat sections on the left. But so I would say this is a useful exercise, so you can also work out what the leader impact is. So, and now that we know this, it's not that hard to check with that. Like this tells us exactly what we're doing, and these plus functions generate our cube algebras. So we just need to verify that relation using this formula on the sheet at the top, degree differential. So,
so why? So that I don't understand this thing you said. So what if you just put all the dv's on the left? Why is that not the right idea?
How do they act? So, sorry. So, like, so like, why don't we just have all the dv's and then what's wrong with this? Well, like f dv equals b and b. So this is a two-sided ideal, and your thing is, and this ring is simple. It has no two-sided ideals. Yeah, I mean, this is just it's like this is the derivation associated to the tangent vector field f times b. This is also the derivation associated to the tangent vector field. And so you see that if you're allowed to change your coordinates, you're allowed to multiply on the left, means you're not going to find any right ideal, which is kind of weird.
The point is that vector field derivations are on the left one. So multiply derivation on the left, derivation multiply the right.
Yeah.
It makes it to the ice.
Okay, so there's no left ideal, but no such right ideal. Okay. So, alright, so this is all the like material which we needed to cover, but I realize I went over it quite fast. So, yeah, no, I would say like if you want to do, like I'll be around after we do some exercises, because like from here, to finish this proof, one would need to just check that the relation holds in these coordinates. And I could write that down, but I feel like that's the kind of thing which you probably get more out of doing it yourself. So force your brain to do that. Okay. So in that case, I might stop there.